Okay, so then the next part of this question, I think we did case 1 and 2, so now we need to do case 3, which is basically case some value between -3 and 3. So case 3 is, so we have case 3 which is basically -3 is less than k less than +3. So the value of the function basically over here we have -2x for this, basically this part of the function for this interval. Negative f of x is equal to -2x. So over here we have f of x is equal to -2x. So then f of k, if k basically, if k is some value between -3 and +3, then f of k would be equal to -2k. Also the limit of there is a problem here that you need to be aware of, and the problem is that basically you're going from -3 to +3, but -3 and +3 are not a part of this interval, meaning that -3 itself is of course not a part of this interval, but any number less than -3 is of course a member of this interval. But as you can see, I don't remember. Okay, now as you can see, there is something interesting here that happens, and there is a question that might arise in your mind, that what happens at the two ends of this interval when you want to take the limit of basically, suppose that you have basically, suppose that you go from, I don't care about the outputs of the function, but here is 0, here is basically -3, and here is +3. And x is some value between -3 and +3, meaning that you have basically, you have some value between -3 and positive. So this is the values of, this is the possible values of x. Of course, -3 and +3 are not a part, members of this interval. And of course, to show that basically f of x is basically continuous in this interval, you have to show that the limit exists at every point here, and also the value of the function is equal to that limit. Now you can imagine that basically you can get, of course, -3 itself does not belong to this interval, so we don't have to, so it doesn't make any sense to take the limit of the limit of the function at -3. But then, since we are working with the set of real numbers, it doesn't make any sense for me to say that, for example, what is immediately after, if I'm moving basically towards the right, towards negative x's, towards positive x's, what is the number immediately after -3? Whatever number I choose after -3, which is even an epsilon greater than -3, again I can find some number that is between -3 and that number. And if I get closer to -3, again I can suppose that, meaning that, suppose that, for example, this is -3, and I choose some number over here, any number over here, call it a, for example, and the distance between these two numbers is an epsilon. And you can imagine that this epsilon is a very tiny distance, meaning that the tiniest distance that you could imagine, which is of course not very clear what I'm saying, but the tiniest, imagine that the tiniest interval, the tiniest distance that you can imagine. Now, however tiny this distance might be, or let's say that basically this a is a number which is immediately after -3 when I'm moving towards positive x's. Even if basically a is a number in the set of real numbers immediately after -3, I can imagine that there is some interval epsilon, for example, or there is some distance epsilon between -3 and a, and still I can divide that a into as many equal distances as I want, and then still there will be more numbers between -3 and a, and by the same logic I can again go further and get closer and closer to -3, but again, however small basically epsilon might be, that epsilon I can again break it down into as many equal distances as I want. And so what that means is that as far as basically the concept of limit is concerned, you can, without any problems, you can take the limit of all of the numbers in this interval without any problems, meaning that it's just not possible, meaning that if I could say that, for example, in this interval, of course -3 and +3 are not members of this interval, but then I can imagine that, for example, immediately after -3 there is some number which is, well, immediately after -3 when I'm moving towards positive x's, and then for that number the left hand limit does not exist. But this number by definition, this set of real numbers does not exist because because however small the value, the distance is between any number that I pick in this interval and -3, there is still some epsilon between that number and -3, and this epsilon I can break it down into as many equal distances as I want, and then still I can get closer to a, I can get close to a from the left, I can get close to a from the right, and still the limit of a is defined, so we have no problem there. And that's actually something that I was thinking about, because if I can say that there exists a number immediately after -3 in the set of real numbers, which is not possible, then the left hand limit of that number does not exist, and then the whole thing doesn't work, meaning that if the left hand limit does not exist, the limit does not exist, and therefore then the function is not going to be continuous at that point. But that point actually doesn't exist, so it's actually, the whole thing actually does work like it just does work. I mean, you cannot find any flaws with the as far as this case is concerned, you cannot find any flaws with the concept of limits. So which means that basically if k is some number between -3 and +3, then f of x is equal to -2x, and therefore f of k is equal to -2k, and then the limit of basically, and remember that I'm working with an interval, so I don't have to worry about basically getting closer from the right and left, so I can just simply calculate the limit. So the limit of f of x as x tends to k would be equal to the limit of basically negative 2x as x tends to k, and that would be equal to negative 2k. And therefore the value of f of x is equal to the limit of f of x as x tends to k, which is equal to negative 2k. And therefore for all k between negative 3 and positive 3, basically f is a continuous function. F is continuous, right? So that is basically that. So this is case 3. Now case 4 is at a point. Case 4 is at the point, and the point is basically this point over here, which is at x is equal to positive 3. K is equal to positive 3. If k is equal to positive 3, that means that then f of x is equal to 6x plus 2. But then we have to be careful about the limit. So basically if x is greater than or equal to 3, then f of x is equal to 6x plus 2. For x is less than 3, then you have negative 2x. So but when x is equal to 3, then 6x plus 2. When x is equal to 3, then f of x is equal to 6x plus 2. And when x is some value between negative 3 and 3, then f of x is equal to negative 2x, right? Is equal to negative 2x. And therefore for k, when basically at k is equal to 3, f of k becomes basically 6k plus 2. F of k becomes 6k plus 2. Now the left-hand limit of f of x, the limit of f of x as x tends to 3 from the left, is basically you have to go for values less than 3, meaning that you have to essentially go for this value over here. You have to go for this clause of the function, which means that you have to find the limit of negative 2x as x tends to 3 from the left. Or actually you don't have to write the left anymore. So the limit of negative 2x as x tends to 3, which is equal to negative 2 times 3, which is equal to negative 6. And by the way, over here, since k is equal to 3, this is equal to 6 times 3 is equal to 6 times 3 is equal to 18. 18 plus 2 is equal to 20, right? And that is the value of the function way up here, right? That is the value. That is the part of the function that we couldn't actually show here. That's 6x plus 2. That's the line with the slope 6. And that is basically what that is for exactly at k is equal to 3. Now, for basically, of course, I can show you the function on a graph, but on my own graph, I have some problems with the space up there, so I cannot show it over there. Now, the limit of basically f of x as x tends to 3 from the right is the same thing as the limit of, so So you have to basically use this part of the function, which is essentially 6x plus 2. 6x plus 2. The limit of 6x plus 2 as x tends to 3, which is equal to 6 times 2 is equal to 18 plus 2 is equal to 20. And as you can see, the limit of the function at the limit of f of x as x tends to 3 does not exist. Does not exist because right here, because you have this line over here that goes from negative 3 to positive 3, and then for x is greater than or equal to 3, then you'll have a line which is 6x plus 2, which is essentially some line that starts up here, and it has a slope like this, something like this. It has some slope like this, right? And so basically you have something like this over here. So, and the value of your y over here is equal to 20, as it seems the value here y is equal to 20. So that's why there is discontinuity here, and the value down here is some value like negative something, is negative with negative 6, over there is 20, so there is discontinuity here. And therefore at x is equal to since this limit does not exist at x is equal to 3, basically f is not continuous. Is not continuous. So this was case number 4. Now we have basically case number 5. We have case number 5, and that is when k is greater than 3, meaning that this part over here where k is greater than 3, right? So if k is greater than 3, then f of x is equal to 6x plus 2. Then f of x is equal to 6x plus 2. So if k is greater than 3, so that means that then for all k greater than 3, f of k is equal to 6k plus 2. Is equal to 6k plus 2. And then the limit of f of x as x tends to k is equal to the limit of 6x plus 2 as x tends to k, and that is equal to 6k plus 2. And therefore you can see that basically f of k is equal to basically the limit of f of x as x tends to k, and therefore for x is greater than 3, then basically f is continuous. And so basically what we found here was that basically your function is continuous here at x is greater than 3, your function is continuous. For this interval less than negative 3 is continuous, at negative 3 is continuous, between negative 3 and positive 3 is continuous. The only point of discontinuity of this function is at x is equal to 3. That means that then basically the only point of discontinuity of f, the only point of discontinuity of f is x is equal to 3. Now, as you can see, of course, there is all kinds of calculators that would tell you in just a fraction of a second all of this information, that's where the function is continuous, where it's not, and so on and so forth. It took us like about 40-50 minutes to consider all of these cases and everything. A computer can do this in 2 seconds, not even 2 seconds, a fraction of a second. But then a computer that computer has been programmed by a human being that understands all of these concepts, and then that computer has been programmed by that human being, and then the computer can do that, of course, much faster. Okay, so now let's do the next question. The next question is question number 8, which is basically f of x is equal to the absolute value of x over x. Question number 8, f of x is equal to the absolute value of x over x if x is not equal to 0, and 0 if x is equal to 0. And you want to find all of the points of discontinuity of this function. So basically what happens in this function, I suppose this function gives you a positive output if your let's see what happens. So if x is not equal to 0, that means that for all of x's from negative infinity to positive infinity, except for x is equal to 0, when x is equal to 0, your output is at 0. Yeah, right? So that is basically your output here. And then if x is not equal to 0, meaning that either x is positive or negative, then f of x is equal to the absolute value of x over x, which means that basically you get 2 cases over here. If x is greater than 0, then basically the absolute value of x is equal to x, and then if x is less than 0, then the absolute value of x is equal to negative x. If the absolute value of x is equal to x, then basically the absolute value of x over x is going to be equal to x over x, which is equal to 1. If the absolute value of x is equal to negative x, then you have negative x over x, which is equal to negative 1. That means that basically for x's greater than 0, your output is 1. For x's greater than 0, your output is 1. And so that then you get some function like this, and for x is less than 0, your output is negative 1. So your function essentially will be something like this. So this line over here is y is equal to 1, and this is y is equal to negative 1. So this is x and this is y. So you can see that basically this function from negative infinity to 0 is of course continuous. It's a straight line, it's a constant function, a straight line with slope 0, so it's continuous here. But then at x is equal to 0, your function, the value of the function is 0, the right hand limit of the function is positive 1, the left hand limit of the function is negative 1, and therefore the limit does not exist, and the value of the function is not equal to any of the right hand limit or the left hand limit. So basically at x is equal to 0, your function is not continuous. So then you can say that basically the function is not continuous or you can say that basically the only point of discontinuity of this function is x is equal to 0. But we will find out. So we will basically consider 3 cases here. We will consider basically basically case 1. We will consider case 1, which is, we take the first case as k less than 0, or you can say that basically let k belong to the set of real numbers, meaning that k is any real number. If that is the case, then basically we have 3 cases. Case 1, k is less than 0. Case 2, k is equal to 0, and case 3, k is greater than 0. Now, if this is if I consider case 1, considering case 1, k is less than 0, case 1, k is less than 0, we have basically the value of the function at for this f of k would be equal to basically so you have f of x is equal to, over here you have f of x is equal to the absolute value of x over x, for x is not equal to 0. So now since k is less than 0, then basically the absolute value of x is equal to negative x. Negative x over x is equal to negative 1. That means that the output of the function is negative 1. F of k is equal to negative 1. And also the limit of basically the limit of f of x as x tends to k is equal to the limit of negative 1 as x tends to k is equal to negative 1. So these two values are the same and the limit exists. So then you can say that the limit of f of x as x tends to k is equal to the limit of is equal to the value of the function f of k is equal to negative 1, and therefore f is continuous for all k less than 0. Now if k is equal to 0, case 2, if k is equal to 0, we have f of 0 is equal to 0. F of 0 is equal to 0. We have f of 0 is equal to 0. And you need to you need to pay attention to the fact that we are talking about a point. Whenever you're talking about a point, usually in these types of limits, you have to approach that point from the right and from the left, meaning that, for example, as you can see over here, I calculated this limit as I didn't approach basically each of the points belonging to this interval. I didn't approach them from the right or left because it was not necessary. But here it is necessary for me to consider the limit of this of f of x at x is equal to 0, and I need to approach 0 from the right and left, because as you can see, the value of the function over here is some other value. The value of the function over here is some other value, so the limits are going to be different. So basically then I can say that at x is equal to 0, then f of 0 is equal to 0. So that's the value of the function. And the limit of f of x as x tends to 0 from the right is equal to, you have to of course go with the value of the function on the right, which is y is equal to 1. So you have to take the limit of 1 as x tends to 0, which is equal to 1. And the limit of f of x as x tends to 0 from the left is equal to the limit of negative 1 as x tends to 0, which is equal to negative 1. And as you can see, the limit of f of x as x tends to 0 from the right is not equal to the limit of f of x as x tends to 0 from the left, and therefore the limit of f of x as x tends to 0 does not exist. And since the limit does not exist, you can say that f is not continuous at x is equal to 0. So that's one thing. So at x is equal to 0, the function is not continuous. Now case 3 was okay, so now case 3, basically we said that for k greater than 0, and over here you can see that if k is greater than 0, the output of the function becomes f of x is equal to 1, right? So over here you have f of x is equal to 1. That means that you can say for k greater than 0, then f of k is equal to 1, right? And then basically we have the limit of f of x as x tends to k is equal to the limit of the limit of 1 as x tends to k is equal to 1. So you can see that the limits are the same, or that these two values are the same. So then you can say that for k greater than 0, f of k is equal to the limit of f of x as x tends to k is equal to 1, and therefore for k greater than 0, f is continuous. And therefore you can say that basically the only point of discontinuity of f is x is equal to 0. That was question number 8. Now question number 9. Question number 9, we have another function. F of x is equal to basically x over absolute value of x if x is less than 0, and it's equal to negative 1 if x is greater than or equal to 0. So that's your function. And if you graph this function for x less than 0, you'll get x over the absolute value of x. So the absolute, when x is less than 0, then the absolute value of x is equal to negative x. And so the x over the absolute value of x is equal to x over negative x, which is equal to negative 1. That means that for x is less than 0, your output is negative 1, which means that you'll get a function like this. So if this is y is equal to negative 1, for x is less than 0, you will have this output. Now for x is greater than or equal to 0, your output is, for x is greater than 0, your output is again at -1. So it just means that basically your function is continuous all throughout the function, meaning that basically for x is greater than or equal to 0, for x is less than 0, your output is -1. For x is greater than or equal to 0, your output is -1. So basically then your function, there is no discontinuity in the function. And I don't really know if we have to really consider any cases here. So this basically, you can actually, what you can do, since the function is giving you the output -1 for x is less than 0, for x is greater than or equal to 0, you can simply say that f of x is equal to -1, x belonging to the set of real numbers. We can write it this way. And of course, you know that this function is continuous all throughout. It's basically this function over here, and this function is continuous all throughout. That means that f is continuous for all real numbers. Of course, I haven't examined this, but you intuitively know that this function is continuous for all real numbers, meaning that this function over here, this basically, you know that first of all, f of x is equal to -1 for basically for every x belonging to the set of real numbers. And moreover, what you have is that the limit of f of x as x tends to basically, you can write it this way. So let me take x, let k belong to the set of real numbers. Now at basically, therefore, we can say that f of k is equal to -1, right? F of k is equal to -1 if k is any real number. And moreover, the limit of f of x as x tends to k is equal to the limit of -1 as x tends to k is equal to -1. And therefore, for all x belonging to the set of real numbers, or for all k belonging to the set of real numbers, at the f of k is equal to the limit of f of x as x tends to k is equal to -1, and therefore f is a continuous function. So that's basically that. Meaning that the function doesn't have any points of discontinuity. The next thing that we have here is 287. The next thing that we have here is question number 10. Question number 10, which is basically f of x is equal to x plus 1 for if x is greater than or equal to 1 and it's equal to x squared if x is less than 1. If x is less than 1. So you can draw the graph of this function as follows. If you have basically f of x is equal to x plus 1, that's the line, basically f of x is equal to x, but shifted up 1 unit, meaning that the line goes through this point. If I take this as y is equal to 1, and then the slope of the line is 1, so the line will go through these two points, and this is for x is greater than or equal to 1, so I can leave it over here, greater than or equal to 1. That gives me this point over here, and then the rest of the function is not that important. Then f of x is equal to x squared. F of x is equal to x squared for x is less than 1. X squared would be basically this point over here, and so I think the function is not continuous at x is equal to 1, as I can see, because the function comes all the way up to here, but then over here we have a problem. As you can see, over here I have a problem. So basically what happens is that basically at x is equal to 1, f of x for all x is less than 1, your f of x is equal to x squared, which is basically this part of the function here, and for x is greater than or equal to 1, your function is x plus 1, which is basically this line over here. So then we can examine this function from negative infinity to 0 at 0 and greater than 0. So then if I make then an assumption that, for example, let k belong to the set of real numbers, then I have 3 cases. Case 1, let's say that k is less than 1, and case 2, let's say that k is equal to 1, and case 3, let's say that k is greater than 1. And basically we can now consider these cases one by one. Case number 1, that is basically k is less than 1. That is k is less than 1. And for these case, basically f of x is equal to x squared. Which means that basically f of k in this case becomes k squared. And the limit of f of x as x tends to k is equal to the limit of x squared as x tends to k is equal to k squared. So as you can see f of k is equal to the limit of f of x as x tends to k is equal to k squared, and therefore f is continuous for all k less than 1. For all k less than 1, f is continuous. You have no problem there. Now at k is equal to 1, it's a little bit different. So this is case 2. Case 2, k is equal to 1. At k is equal to 1, the value of the function is x plus 1, right? So at k is equal to 1, f of x is equal to x plus 1. Therefore, f of k is equal to k plus 1, which is 1 plus 1 is equal to 2. F of 1 is equal to, what I mean is that f of 1 is equal to 2. So if f of 1 is equal to 2, so what that means is that f of 1 is equal to 2, and therefore now at basically at k is equal to 1, I can say that basically f of 1 is equal to 2, and the limit of f of x as x tends to 1, meaning that tends to k, is, and of course I have to consider that from the right or left because it's a point, right? So from the right, the limit of the function becomes, I have to consider that using this line. This is for x is greater than 1. So I have to take the limit of x plus 1. That's the limit of x plus 1 as x tends to 1, which is equal to 2. Which makes sense, it's equal to 2. And the limit of f of x as x tends to 1 from the left is equal to the limit of, so I have to take this part over here, which is basically x squared. So I have to take the limit of x squared as x tends to 1, which is equal to 1. And as you can see, the limit of f of x as x tends to 1 from the right is not equal to the limit of f of x as x tends to 1 from the left, and therefore the limit of f of x as x tends to 1 does not exist. Therefore, f is not continuous at x is equal to 1. That was case 2. Now case 3, we said that that's for x's or k is greater than 1. That's for k is greater than 1. Now in that case, basically we have f of x is equal to x plus 1. We have f of x is equal to x plus 1. And so f of k would be equal to k plus 1. F of k would be equal to k plus 1. And the limit of f of x as x tends to k would be equal to the limit of basically x plus 1 as x tends to k is equal to k plus 1. K plus 1. And therefore f of k is equal to the limit of f of x as x tends to k is equal to k plus 1, and therefore f is continuous. F is continuous for all k greater than 1. And so you can say that basically x is equal to 1 is the only point of discontinuity, is the only point of discontinuity of f of x of f. That was question number 10, I suppose, right? But it doesn't make any sense. Okay, so it turns out that I was solving some other problem other than question number 10 in the book. So the question that I was solving was basically this one, and this is correct. The way that we have solved it, it is correct. But the problem that was actually in the book was f of x is equal to, and I was kind of astonished to see the result, f of x is equal to x plus 1 for basically for x is greater than or equal to 1, and it's x squared plus 1 for x is less than 1, right? And you can imagine that if you have this line f(x squared), and if it is shifted up 1 unit, these 2 points will be the same, meaning that these 2 points will be joined. Right now this output is at x is equal to 1, then it goes to output is equal to 2, and so your function will be continuous over there. And of course for that, of course we will do that in the next video. We will do this exercise in the next video as well. But this function has no points of discontinuity. This function, this does have a point of discontinuity because of what you can see over here. So what we were doing right now is actually not question number 10. It's just something that I forgot to write the plus 1. I didn't actually see this plus 1 over here. And so I solved this problem, which is a variation of this problem, and this has a point of discontinuity at x is equal to 1. But now in the next video, we will also talk about this problem. These are, well, these are the kinds of problems that basically deserve a little bit of our time. You learn a little bit of something from here, something from there, from these examples. So I'll end this video here. The problem that we solved here, this problem, the problem is completely valid, and we solved the problem right, and the answer is also right. But then the actual question number 10 is basically this problem here that we will solve in the next video. I'll see you in the next video, and thank you.